Hello and welcome to the section 8.2 lecture. Today we're going to be talking about solving systems of equations using substitution. We've talked about graphing systems of equations. That's one method, but it's not what we consider to be an algebraic method because of the fact that it's really a graph and check method. We want ways to do these problems that are solid and give us true solutions. Not something that we have to go back and check at the end. So getting right into this, the basics of the substitution method revolve around the idea that we can solve for one variable and then once we have that, maybe we say that we have something like x equals some stuff, okay? And there may be y's involved in what it equals. There may not be. But even if there is, that's not a big deal. We can find out what x equals and then plug that in to find the other variable. And we'll run across this from time to time where we get an equation like this. We say 4x plus 6y equals negative 24, and they give us another equation, some other scenario that basically says that x is equal to 3. And so how do we deal with that? What do we do with that? Well, what we would end up doing is, now that we know that x is 3, I can plug it into this equation for x and figure out what y is. All right, now the way that looks is that I'm going to have 4 times 3 plus 6y is equal to 24, negative 24. 4 times 3 is 12, plus 6y equals negative 24. And I'm going to be subtracting 12 on both sides. And we get 6y is equal to actually negative 36. And if we have 6y equals negative 36, I can then divide by 6 to cancel out my 6's and get that y is equal to negative 6. So we get the answer, part of the answer from the problem. They gave us a little bit. We get the answer 3, negative 6. Our answers aren't going to change. We're still thinking of this as a point where two lines are going to cross. And that's what we have here. Okay, we have the point 3, negative 6 is where these two lines will cross. Okay. Now there's multiple ways that we can see these types of problems. This is a very basic problem when it comes to substitution. We don't even really think of this as substitution. But what we want to do is we want to solve an equation for a variable and then plug that variable into the other equation and work our way from there. Now, a very specific scenario, actually I'm going to show this first. This is sort of the step-by-step process that it takes. And it says to solve a linear system by substitution. Step 1 is we want to solve one of the equations. So again, one of the equations for one of its variables. And we have choices to make there. We can go with equation A or B, if you will, and we can solve for either x or y. Okay, then once we have that, we're going to substitute the expression. Now, in the first problem we did, it wasn't an expression. It was just a number. It was that negative 3. But typically, we'll have an expression. We're going to substitute that into the other equation, and that's important. You can't substitute it back into the equation you have because that's not going to tell you anything. It's basically going to turn into like a 0 equals 0 type of scenario. So we want to substitute it into the other equation and solve for that other variable, and then we substitute the value we get from step 2, and we'll get into all these. But basically, you take your answer for one of the variables, plug it into one of the equations, and figure out the missing variable. Okay? But it's probably easier to see what those steps really mean based on an example. So in this case, step 1 is done for us. I already have one of the equations, and technically here I have both equations solved for one of the variables. But I'm going to consider that I'm solving this top equation for y. And that, again, that's already done for me. I have y by itself. So y is equal to this mess, this negative 2x minus 4. So step 1 is done. It was done for us originally. Step 2, I'm going to plug this quantity, this expression, in for y in the other equation. And what comes from that step is what makes this strategy so kind of monumental and why it makes it helpful. Because you notice right now, what does my equation have? I should say, what does my equation only have? Okay, my equation only has x's. So I can solve for those x's. All right? And we're going to do that by, really, is that what that is? Okay, here we go. I'm going to add 2x to both sides. Oh, I guess it works out. I was thinking ahead, and I never think ahead very well. 4x plus 2x is 6x plus 14. So I want to subtract 14 from both sides. On that side they cancel, and on this side I get 6x equals negative 4, and negative 14 is negative 18. And I'm going to try to fit it in here. It might get a little bit sloppy, but I'm going to divide by 6 on both sides. And I end up with x is equal to negative 3. And all that is step 2. Step 2 is the longer step in this strategy. Step 3 is going to be to take this answer and then use one of the equations that I have to figure out what y is. And there's a big advantage to using substitution at this point. Okay, and that big advantage is that right now technically I have 2 equations, but I have the equation that I came up with, so to speak, the y equals negative 2x minus 4, already solved for y. And so when I plug a number in for x, this is what I get. Y is equal to negative 2 times my negative 3 that I had right here, minus 4. Okay. And at this point, solving this equation isn't really, it's almost weird to call this solving an equation because it's really not. It's what we would consider to be evaluating. Because solving includes like moving numbers to the other side of the equal sign. This doesn't have any of that. This just has multiplication and subtraction. So here I get 6 minus 4, which is 2. And so y is equal to 2. So my answer is the negative 3 for x and the 2 for y. That's going to be the point where those 2 lines cross. But again, even that's a very special case of this method because they put both the equations in slope-intercept form. And we might think to graph that, but we do have to have a graph that at least goes to 14 on the y-axis to get my y-intercept on there. So a lot of people would still rather do this algebraic method as opposed to coming up with a graph that was big enough. Okay. So slowly escalating the difficulty here and just getting it out of the way. I typically won't do step 4 when I do one of these methods. I'm not going to check my answer. Probably not the best idea. I probably should check my answer. But really, I already did it once. Like, this is half of the check right here. But I plugged 3 in and I got 2. I could check my math on that, sure. But the real check would be going back to this equation and plugging in my -3 for x and seeing if I get -2. Or +2, sorry. And you can do that kind of informally, especially on this one. Because 4 times -3 is -12. -12 plus 14 is +2. So we're good. Okay. Now I want to take a look at this one. I'm going to take this value right here because it says this is y. This bottom equation says, hey, this is y. And I want to plug that in for y in the other equation. So again, step 1's kind of done for me. So I'm going to take 5x minus, and I'm going to switch colors here. Because I have this as what y is equal to, a lot of times I'll put what I'm substituting in parentheses. That's a pretty common theme for me. It just kind of highlights like what I'm doing. Not only did I put it in a different color, but I also put it in parentheses. And I actually do that for a reason. Because especially in a problem like this, I have minus, which really means that I have to distribute that negative. And for me, I know that if I don't put parentheses there, I'm going to forget to distribute. So we want to make sure that we do that. So I have 5x. -3 is +3. -18 is +18. And then that's going to equal a -22. Combine my like terms. 3x's and 5x's is going to be 8x's. Plus 18 is equal to -22. Subtract 18 from both sides, and it looks like we're going to get somewhat of a large value here. But 8x, I don't like that, that's ugly. Yuck. But I'm left with 8x is equal to, what is that, -40. So it does all work out in the end that when I divide by 8 on both sides, I'm going to get that x is equal to 5. Now that I have what x equals, go back and plug that in to one of my original equations. I can pick either one, but there's definitely a smarter option between the two possibilities. I would rather use this one because, again, there's no equation solving that's actually going to take place here. It's going to make life pretty nice. So I get y equals -3 times 5 is -15. And then minus 18, and that might be tricky. I'm not going to say that you can't use a calculator, but it's going to be -33. So I get an answer. X is 5. Y is -33. Okay? And that would be my answer there. Again, looking for the point where the two lines cross. So the question always comes, is graphing or substitution easier? And it's totally up to you. I can tell you that substitution is always going to give you the exact answer. There's no definite reason to check. You should kind of always check the like making sure that your answers make sense. And like in this one, I totally believe it because I had a y-intercept of -18 here and a y-intercept of 22 here. So I could understand that my y-intercept is big. So that kind of follows suit with what the problem showed. But looking at this, we can do both methods. And this really shows kind of the severity that these problems can get to. So I need to pick one of my equations, A or B, and solve for one of the variables, X or Y. Personally, I'm always looking for, when I'm dealing with substitution, I'm always looking for an equation that has a variable with no number in front. Okay, and I notice that A has both variables don't have a number in front. And the reason for that is if I pick that I'm going to solve A for X, which I can do that, I can take X plus Y equals 5, and I can solve it for X. And to do that, all I have to do is subtract Y. And even if Y was being multiplied by something, that's still all I would have to do. Now, I do write this a little bit funky. I'm going to say that X is equal to 5 minus Y, so that I don't have to deal with a negative Y plus 5. You can write it either way. But I noticed that since I picked X that didn't have a number in front, I don't have to divide by anything right now. That's why that's what I'm really looking for. I'm really looking for an equation that doesn't have a number in front of at least one of its variables. Okay, once I have that equation, I'm going to stick with that. I'm going to solve that and pick that one and solve it. So now that I have what X equals, I know that X equals 5 minus Y. And now it is important to note that I did solve this equation. So a lot of times I'll actually do this. I'll say, I'm going to solve this equation. And maybe I'll say I'm going to subtract Y, so that I don't go back and try to plug it into this equation. Because again, that's going to just give me a 0 equals 0 kind of solution. Okay, it's not actually going to give me an answer. Okay, so I have to plug it into the other equation. And I'm plugging it in for X because it's what X equals. So let's go ahead and do that. I have negative 5 times 5 minus Y minus 7Y equals negative 21. A lot of negatives in this problem, but that's okay. Negative 5, so I do have to distribute since I have a number outside of parentheses. Negative 5 times 5 is negative 25. Negative 5 times negative y is plus 5y. Minus 7y equals negative 21. Combine my like terms on the same side, and I get negative 25 minus 2y equals negative 21. Add 25 to both sides. I'm just solving equations here. Over here they cancel, and I get negative 2y is going to be equal to positive 4. And we can give ourselves a little more room. Divide by negative 2, and we should get that y is equal to negative 2. Now that I have what y is, I do need to find what x is, but I do have an equation that makes that very easy, this equation right here. If I take that and I plug in my negative 2 that I found for y, that makes life pretty nice. 5 minus negative 2 is really 5 plus 2, and x is equal to 7. So my answer here should end up being 7, negative 2. If I look at graphing this, and again, this was all about which one is easier. Is it easier to graph or to use substitution? Granted, this is a lot of math work. There's a lot going on here. And I would say that that's not always the case when it comes to graphing. But there is one issue with graphing, and we're going to see it here in a second. If I use the cover-up method, then it's a little bit easier to graph this. There's a little bit less math work to do. If I decide to turn these into slope-intercept form, then I'm really doing like half the work that it would take to do substitution. So I'm going to try to show that even though I'm going to use the intercepts method, cover up the y, and I get x equals 5. That's right here. Cover up the x, and I get that y equals 5. That's right here. That one's pretty easy to graph. And I'm probably going to have to, oh no, that's not bad. I might have ruined it a little bit at the end there. Let's try to do as good of a job as we can on getting a straight line that goes through my 2 points. Yeah, I'm good with that. Okay, and then for my other one, this one's where the tricky part comes in. If I cover up the y, I get negative 5x equals negative 21. And I have to solve that equation. And it's not clear to me what it is. Okay, when I divide by negative 5, I would get that x is equal to positive 4 1/5. Right? Yeah, positive 4 1/5. And that right there is pretty tough to graph, but we can give it a shot. X equals 4 1/5. I'm going to say that's about right there, kind of towards the right of that point. I know it's kind of hard to see where it is exactly because it's a pretty small graph. Although when I cover up the x, I do get negative 7y equals negative 21. So negative 7y equals negative 21. And for that, I would divide by negative 7, and I get a nice answer there. I get that y is equal to 3. So the y-intercept is here at 3. Now, when I try to make a straight line through those 2 points, and trust me, I picked this problem for a reason, even though those were some ugly, that second one was kind of an ugly line to graph. It's really hard for me to tell exactly where these 2 lines cross. Now, if I assume that it has to be at a whole number, then it's then it's a little bit easier to tell. But if I don't assume that it's a whole number, which I really shouldn't, then it's tougher to tell. It actually looks like it misses that point 7, negative 2. Looks like it misses it kind of on the lower right side. But that was just really a graphing error. So that's what a lot of these come down to. All right, let's look at some examples. Seeing how many I got. 6 is good. Okay. And each one of these, and each one of these 2 levels here, show the 3 different types of problems that I see. So I want to take a good look. Actually, I lied. Not really. But I do want to take a look at all of them. Because it is a possibility that we just have problems that are set up better for substitution. And in fact, for me, when I see 2 problems, two equations that are both in slope-intercept form, sure, I might want to graph them, but I don't want to get a graph that goes to negative 22 or to negative 17. So I don't really want to graph that because it's going to take a lot of work just to build my graph. Sure, I could grab some graph paper and do it that way, but it's just, I would almost even argue it's easier to take this and put it in for this y right here. And that's what we want to do. I'm going to say negative 4x minus 22 equals negative 3x minus 17. And we can move whichever x we want. Maybe we want to add 3x to both sides. And I'm going to do this other part at the same time. I'm going to add 22 to both sides as well. At this point, I assume that we can handle a step like that. Sort of a combination of 2 steps. Over here, my x's cancel, and over here, my 22's cancel. And I get a negative x. Negative 17 plus 22 is 5. So that really means that x is equal to negative 5. Now I use that negative 5 in any of my equations up top. Okay, you might be urged to pick the one that you had solved for y. We didn't really have to solve any of them for y because they were already done. But it's really just pick your favorite one. And in the long run, I would almost say don't be picky, just go with one of them rather than sitting there and wondering, which one should I pick? I don't know. When in doubt, just pick one. We have negative 4 times negative 5, which is 20, minus 22, and that equals negative 2. So my answer will be x at negative 5, y at negative 2. That actually didn't involve too much work. Okay, let's look at our next one. I'm trying to find an equation that's either solved for a variable or has a 1 in front of a variable. And when I look at it, I have this equation solved for a variable. That's what y is equal to. So I'm going to put that in for y in the other equation. 5x minus 5 times all this, 2x minus 4, equals 10. And now I need to distribute. I do need to distribute a -5. I need to remember that as I'm working through this problem. That's probably one of the most common errors, is that we forget that that's a -5. We just treat that as a minus, and we forget to distribute it. -5 times +2 is -10x. -5 times -4 is +20. I've got a 5x and a -10x. That's going to be a -5x. And at the same time, I'm going to subtract 20. And that's going to equal 10 minus 20 is -10. And we can divide by -5. X is now going to equal +2. Oops, not done yet. Started treating that like I was done. Got excited. So with x equal to 2, I'm going to pick my first equation that says that y equals stuff. 2 times 2 minus 4. 2 times 2 is 4. 4 minus 4 is 0. So y is equal to 0. I get the point 2, 0. That's where those two lines cross. All right, let's look at this next one. Again, looking for an equation that's solved for a variable. This one tells me what y equals. It's in slope-intercept form. And I'm going to plug that in for that y up there. 4x minus 3 times all of that equals 21. Distribute. 4x. -3 times x is -3x. -3 times -7 is +21. Equals 21. And it looks like a cool thing's going to happen. Number one, 4x minus 3x is just x. 20 and subtract 21 on both sides. 21 minus 21 is 0, so x is equal to 0. So now I'm going to use that in my really second equation here that already says what y equals. 0 minus 7 is -7. So they intersect at the point 0, -7. Okay, go ahead and pause the video and get these 3 problems done. Hopefully you had a chance to do that. As we look at these, looking at my first one, similar to the other ones that I've seen, I have y solved for a variable, or I have, an equation solved for the variable y. So I'm going to plug that in. And a lot of these problems have been the same, I understand that. But we do have some variation down the road here. So I'm okay with it. And there's some ugly numbers in here. This would be a tough one to graph. Okay, just because I'd have to get y-intercept to -22. But same process, distribute. Remember that you're distributing a negative. -8 times -7 is -56. -8 times -22. Let's just double check ourselves on that one. 8 times 22. And it's a negative times a negative, so it is a positive 176. Equals -13. Now I will combine my variables. That's going to be a -63x. And I know that eventually I'm going to have to divide by negative 63. So I might grab a calculator if I don't have one yet and even check my work on this. Really, that's a negative 13 and 176. So I'm going to go 13 plus 176 because my calculator doesn't do negatives very well. And that's 189, so it's a negative 189. Okay. And now I need to divide that negative 189 divided by negative 63, which is going to give me a positive, and it's positive 3. So after all that ugly work, it came out with a pretty nice answer, x being x being positive 3. So then we have 7 times 3 minus 22. 7 times 3 is 21. And 21 minus 22 is negative 1. So I get the answer 3, negative 1. Okay. Next one, pretty straightforward because they actually already tell me what y is. I know that y is negative 8. So that kind of helps me in two different places. Number one, I just get to plug that negative 8 in for y. But also it tells me that wherever these lines cross, the y value is going to be negative 8. Right? I just don't know the x value yet. So let's find it. Negative 3x plus 2 times negative 8 equals negative 7. And in fact, I would say a lot of equations are this way. A lot of just solving equations could be written this way. If you say something like 2x plus 5 equals y, and then you say something like y equals 13, then really that system of equations simplifies to 2x plus 5 equals 13. And then you're just solving this equation. Granted, this is an easier form of what we have here, but it's really just showing that almost all equations, all single variable equations, could be written as a system of equations. But they're only asking for one answer. So anyways, going back to this, I'm going to rewrite that actually. 2 times negative 8 is negative 16 equals negative 7. I'll add 16 to both sides. Over here they will cancel and I'll get negative 3x is equal to, that looks like 9. Divide by negative 3. And we get that x is equal to negative 3. So the point where those two lines cross is actually negative 3, negative 8. I don't have to go back and solve for y because they already told me what y is. This is probably the toughest form of this type of problem. I have to solve, I actually have to do step 1 here, which kind of an oversight on my part that we haven't looked at more of these, but mainly because of the fact that if I ever were to see a problem like this, I probably wouldn't go right to substitution. I would probably do another strategy, okay? And we'll talk about that tomorrow. But I'm looking through this and I'm trying to find an equation that has a variable with no number in front. And for me, I'm looking at that top variable and I'm looking at y because it has no number in front. So I'm going to solve that equation for y. All I have to do to that is add 3x. And so I get that y is equal to 3x plus 6. Now, not only is it in slope-intercept form, but it also tells me what y equals, and I can plug that in for this equation for y. Negative 6x plus 3 times 3x plus 6 equals 9. Oops. Should probably jump back to my other color there. So plugging that in, now I need to distribute. Negative 6x plus 3 times 3 is 9. 3 times 6 is 18. I'll combine my like terms here, and I'm going to subtract 18. Over here, the 18s cancel. These two combine to give me a 3x, and 9 minus 18 is negative 9. Divide by 3. We get that x is equal to negative 3. Hey, kind of like the last one. Okay. Now let's use that x equals negative 3 in the equation that I built. Oh, you can't see that because my face is over it. In the equation that I built right here. So I'm going to rewrite that. Y is equal to 3x plus 6. Sorry, I'm at the edge of my tablet here. And I'm going to use x equals negative 3. So y equals 3 times negative 3 plus 6. And that's going to give me y equals negative 9 plus 6. And that kind of looks familiar as another negative 3. That's okay. They can meet at negative 3, negative 3. That's totally legal. So don't worry, think, I got the same number twice, maybe something's wrong. No, that's good. That's your answer. Okay? So that'll be it for the notes. As far as practice goes, I do want to cut down this a little bit. And I don't want to make it too easy on you, but let's probably go with, let's keep it light. We're getting close to the end of the term here. We don't want to get bogged down. I'm going to say numbers 1, 3, 1, 3, and 5. And then application-wise, I'm just going to say number 3. It is the longer of the problems there, but the other ones are just kind of ugly. And number 3 is a great step-by-step of how to do a true problem-solving type of problem. Okay? All right, that being said, I hope you have a great day, and we'll see you in class.